So I meant to show you this last time because it relates to acceleration. So this is like a kind of like a bouncing ball, and so at the top, is the ball accelerating or not? At the top, is it accelerating? Is it accelerating? On the way up, it's doing what? Slowing down, and then at the top it pauses, and then on the way down it's speeding up, right? Does it slow down, pause, and then speed up? So at the very top, is it accelerating? Some of you are thinking speed. I'm not asking about speed. I'm asking about acceleration. Is it accelerating at the top?
Yes.
Which direction? It's accelerating down because before it's slowing down and then it's speeding up. So it has acceleration at the top, right? But it is going at a constant speed. How is it possible that it's accelerating downward and going at a constant speed at the same time? How is it possible that that ball is traveling at a constant speed, but it's accelerating downward? Yeah, Brian.
It travels at the same speed going up and down, but it has to make stops. So because it made that stop, it had to decelerate and accelerate to start again.
No, it's slowing down and then slowing down on the way up, speeding up on the way down. So when it's at the top, it's accelerating downward. Yeah?
Are we looking at it like a circle? Like how it's staying at a constant speed?
I think he's onto something. How is it that it's traveling at a constant speed, but accelerating downward when it's at the top? Because of?
Circular motion.
We never said centripetal force in this class. What did we learn in this class? Why is it accelerating downward, even though it's going at a constant speed?
It doesn't have a tangential acceleration, it's just a normal acceleration.
Yeah, it's normal. It's turning, right? It's due to turning. So because of it's turning to the right, at the top, it has an acceleration down, right? Perpendicular in a normal direction, perpendicular to the path. So it's all that the acceleration that I showed you. You saw a change in speed. Well, that was due to normal acceleration due to turning, and no tangential acceleration. So yeah, so it's the acceleration that you see when you look at it this way is the normal acceleration, right? It's the acceleration downward. That's downward, so that's perpendicular to the path. Okay. Let's just practice. We were talking about partial derivatives. So I've got z as a function of x and y, and I've got these partial derivatives. The partial with respect to x at x is 4, 7 is 5, and the partial with respect to y at negative 3, 8 is negative 0.5. So we're going to practice interpreting what that statement means, including all the details and being precise, right? Precisely and thoroughly explain that expression and that expression. Everyone's got a partner. You're practicing. One person do the first one. The next person do the other one. How about Joshua? Did you get this? Tell me about this. Partial derivative of x, partial derivative of f with respect to x at 4, 7 equals 5. What does that mean?
X and y, 4 and 7 respectively. For every small change in x, you get a corresponding change in z that's 5 times that change in x.
That's pretty good. Yeah, it's the change in z, right? So these partial derivatives are how much the function changes, which is the z value, with respect to, in this case, x. So yeah, so given a small change in x from 4 at y equals 7, z will change 5 times as much as their change in x, or about that, right? So yeah. So that's giving you a feel for that's the rate of change of z with respect to x. How fast z is changing corresponding to x. For a little change in x, z changes 5 times as much. So this is relatively high, right? It's just like high rate of change. Okay? Somebody new. How about this other one? Sammy, did you get the next one?
The
change dy near the point -3/8, so if you put your value,
Yeah.
the change in z is -0.5 times the change dy.
Yeah, really good. Hear that? So how is y changing compared to x at this point? So if you talk about, if I made a little change in x, z would change this much. If I made a little change in y, how would z change compared to how z is changing if you made a change in x? Does that make sense? Does that question make sense? So how does z change for changes in y compared to how z changes for changes in x at this point this is different points, right? These are two different points. So that would be a valid question if we were at the same xy coordinates, right? But how is z changing if it's negative 0.5 times the change in y? What is it doing? What is z doing?
Traveling downward.
Decreasing, right? The value of z decreases at a rate of half of how y changes, right? For constant x at -3. Okay, so this is we're gonna use this in class as we're working with partial derivatives and kind of building on it. We're gonna use this interpretation to help us kind of form some mathematics and solve some problems. So we want to keep that in mind, right? This is important. Any questions on that? So you watched the video for our fire alarm miss. You should have watched the video at the end, the last 10 minutes or something like that. And did the guitar string function was in there? All right, so this is the surface for the guitar string function. X was like distance down the string, and then y was time. So somehow, the surface, the z values of the surface are showing you displacement of the string at combinations of distance down the string and time. So I've picked this point here, 80.5. So 80 millimeters down the string, 0.5 milliseconds after it's been plucked. Here's that point right there, 80, 0.5. And what I want you to do is I want you to predict, or what can you say about the partial with respect to x and the partial with respect to y at that point by looking at the surface now. So we talked about that there are 4 representations of these multivariable functions, and we're going to talk about partial derivatives in each of those 4 representations, right? So this is now what? The representation of a surface. So what could you conclude about the partial derivatives at that point by looking at the surface? Talk, go. The partial derivative with respect to x. What can you conclude about the partial with respect to x? He said negative. Agree with that? So we're actually asking, really the question we're asking is negative, positive, or 0? He said negative. Do you agree? Some people are agreeing. Does everyone agree? Why is it negative? Because for a positive change in x, which would be coming out at you, right? Z, looking at the surface, z goes down. So negative. Do you follow that?
Yeah.
Okay. Partial with respect to y. Negative, positive, or 0? Y 0. In the y direction, for a change in y, are you heading up, down, or neither for a small change in y? Yeah, this is kind of like a local maximum in the y direction. Do you see that? In the y direction, you're at a local max. So you're basically, z is staying the same for a small change in y there. Therefore, partial derivative is 0. Does it make sense? So that I did another example of that in the supplemental video that would have been what we did if the fire alarm hadn't gone off. So if you haven't watched that, go back and watch that. I do more of this. We actually found the values using algebra, and then we predicted on the graph and showed that they were the same. Okay. Okay, so we've done partial derivatives in the context of the function formula, right? You're using all the same derivative rules, but you're holding the other variable as constant. So we did that. And then we looked at some couple here where analyzing partial derivatives in terms of the surface. So next thing we want to do is look at that one, this one. In terms of a table of values. Okay, so here's a nice multivariable function, and the multivariable function is the heat index. Right? Heat index, how hot it feels, depends on two things. It depends on the actual temperature outside and the humidity. So this is a perfect example of a multivariable function as represented in a table. So given any so given a temperature, say here at 90 degrees, okay, and relative humidity of 45 degrees, that means it feels like, or the z value, the dependent variable of this function is 93. Okay, so it feels like 93 when your temperature is 90 and your relative humidity is 45. Perfect example of a multivariable function, right? Input variables, temperature and humidity. Output or dependent variable is the z coordinate, is what it feels like, 93. Okay, so let's look at some. So here it's when it's 82 with 90% humidity, it feels like 91. Need my pen. Okay. So we're going to estimate partial derivatives. We're going to start with this second example here. So we've got our variables. I is going to be a heat index. And that's unit is what it feels like, so it's going to be degrees Fahrenheit. And then we got our T is going to be our temperature. Also degrees Fahrenheit, but actual degrees Fahrenheit. And then H is going to be our relative humidity, and that's a percent. Okay, so what I want to do is I want to estimate the partial of I with respect to, first of all, T at 82, comma, 90. So this is an estimation. So how will I do that? I want to know the rate of change. So we know that the actual temperature index is 91, but what about the partial of index with respect to temperature? So what could we do to figure that out? What could we do to figure that out? So here I am in the table. So what is this? It's a number that's going to tell us what, like, how much the index changes per change in temperature, right? Per change in temperature. Yeah, Jeffrey.
So what you do is you can kind of move like a little bit up in the positive temperature.
Okay.
And then you can subtract the 2 and then divide it by the change in temperature.
Oh, nice. Okay, so if I move this way, so if I go from here to here, my heat index goes up 7, right? And as that goes up 7, that goes up 7 for a change in temperature of 2. So according to going up from 91, our rate of change would be about 7/2. But now we can also look what's happening below too, which would be just as valid, right? Below, how much does it go up? It's going up 5. for a change of 2. So like maybe our best bet is to average those two. So we have a change of 5 in index and a change of 7 in index, so we'll just call it a change of 6 in index per 2 degrees Fahrenheit, which gives us a rate of change of 3, what's the unit? Degrees Fahrenheit per degrees Fahrenheit. Do I want to cancel those out? Don't cancel them out, right? First, 2 reasons. They're kind of different, right? It's how it feels versus the actual, but also we want to preserve the unit as a rate of change, right? It's how much that changes per change in that. So if you cancel them out, then you have a unitless measure, and rate of change is not unitless, right? Okay, so do the same thing. I want you to predict for the same temperature and humidity. Predict the partial of humidity with respect the partial of index with respect to humidity at that same point. So you do it. And you can do it by yourself or collaborate, whatever you need. Yes, when the humidity goes from 90 to 95, changes by 2. So what should we call our change in index? Like 1.5, right? If we want to average them. So like 1 on this side, 1 on the left side, and 2 on the right side. So 1.5 for change of, how much is the humidity changing? 5. Is that 0.3? And units on that would be? Degrees Fahrenheit feel per percent. Okay, interpret that value. So what does that value mean? Tell the person next to you, everyone practice. What does that number mean? 0.3 degrees Fahrenheit per percent. Okay, Connor, tell me.
So at 80 to 90,
Yep.
for every small change relative to humidity.
Okay, hold on. So Connor's showing us the way here. So he said, go ahead.
At 80 to 90, every small change in relative humidity leads to a change in heat index 0.3 times as much.
Yeah, good. Right. So when we're at the point 8290, every small change in humidity, he said, results in a change in heat index of 0.3 times as much as that. Okay, so other one. Now this one. So I want you to find both. Find the partial of index with respect to temperature. Okay, so let's not go through the math. Let's just come to consensus. What did you get for the partial of index with respect to temperature? What'd you get, Anna? 1.75. Is that a good one? I see lots of nods. Units? Good, okay. And then the partial of H with respect to T. Shout it out, see if we agree. 0.4. Someone else get something different? Are we in a consensus about that? There's a nod. 0.4, yes. I see nods. Those who got something different. Sorry, this is I per H. Is that what you're hesitating at? This is I per H. But the number is good? Okay. Okay, so here we are. It's 90 degrees out, and the relative humidity is 45. And the temperature is going to go down 4 degrees. That's too much. 1.5 degrees. 2 degrees. I promise. And the humidity is going to go up 0.1%. I want you to find the new actual heat index. What will the heat index be when the temperature goes down 2 and the heat index goes up 1? But not using the table, using this. Well, kind of using the table. You're allowed to use that from the table, okay? But nothing else. Use these, the values that you found, and this value from the table to figure out what will the new what will the new heat index be if the temperature goes down 2 degrees and the humidity goes up 0.1%? Let's make it a half. 0.5. That's good. So, this is all about the meanings we've been practicing, right? This is all about those meanings we've been practicing for these numbers. If you can state the meanings of those numbers, then you'll know what to do. You'll know exactly what to do. So if you're stuck, then go back and review what's the meaning of the 1.75. You'll find out this is exactly the problem I'm asking you. What's the meaning of the 0.4? It's exactly the situation I'm giving you, interpreting those meanings. So, what do you think? Travis, what do you think?
I got 89.7.
No. Process, not answers. Process.
So I multiplied that 1.75 over change in temperature.
Why?
-2.
Why did you do that?
For every change in temperature,
Yep.
The temperature you're going to feel is changed by 1.75 degrees. So like the
One
heat
point-
index would change by 1.75 degrees.
Times as much as the change, right?
Yes.
Right? Given any change in temperature. Look, I gave you a change in temperature. What did we say? The change in index will be 1.75 times the change in temperature. Right? So that's, 1.75 times the -2 will give you what? But what will the meaning of that be? Change in index due to the change in temperature, okay? And then what about the change in index for the change in humidity?
I multiplied the 0.4 times that 0.5,
Mm-hmm.
and then add those together, and that gives me the total change. And then I just add that change to that 93. It was originally.
So the total change is what? Anyone got it? 3.3? Okay. Therefore, the new I is, how would we find the new I? The old I? What? Plus the change. Should make perfect sense. So this calculation comes right out of what we said the meanings of these were. Given any change in the variable, the change in the dependent variable will be that rate times your change in independent. So we found the change in the index due to temperature, the change in index due to humidity, and so those are kind of like independent, right? You just add them together. So we get the total change in heat index. This is up degrees Fahrenheit. And then we can just, that's our change. We're going to add it to the old value. So is it 89.7? It's the new field. based on those changes in temperature and humidity, the new field will be 89.7. Yeah.
If it's 0.5%, do we convert that to a fraction?
No, because these are all in percents, right? You're just working in percent here. So there's no conversion to decimal. This is half a percent. Yeah, half of a percent. Okay, doesn't make sense. Really important here. So taking changes together, right? We're taking changes together. And looking at the overall change based on changes in both independent variables. Any questions on that? So I had you do it because it's not like formulas to memorize. Every single step here should make sense. And something you wouldn't have to memorize, but you could do because you understand the meanings of everything. That's the goal. Okay, so notice here I could shifting gears. I could kind of draw lines here at like constant index values. So here's like 95 would be something. 95 would be like along here somewhere like this, right? Right, and then say 86. 86 would be along here like this. See what I'm doing?
Mm-hmm.
And when I do this, when I pick a constant value of index and try to draw a line through here, here's 84. What am I doing? What are those lines?
Contour lines.
Are those contour lines, right? These are like constant z values. So here's 82. I just like doing this. It's fun. Okay, so each of those lines that I drew is like it's all the ordered pairs of humidity and temperature that have a constant index. And so what I'm doing there is I'm like drawing a contour plot. So we want to now look at partial derivatives in the context of, or the representation of a contour plot. So let's look at, no, I want to be here. Just want to zoom out. So here's another cool multivariable function. This function is the wind speed in a tornado, which is a factor of two things. How big the tornado is, or x independent variable is the volume of the tornado in millions of cubic feet. And then my distance from the center of the tornado in hundreds of feet. So depending on the size and how far you are from the center, you get a wind speed. And so that's what this shows. So the dependent variable, or like the z, is wind speed. And so I'm showing that as a contour plot, right? I'm showing it as a contour plot. So let's just start by interpreting this point right here. Go. So can you read this? This is 1. So again, hundreds of feet from the center, and then millions of cubic feet on the x-axis. So interpret that point. Quick, go.
Is the speed in miles per hour?
Yes. Yes. Thank you. So now, that was just warm up. So when the tornado is 2 million cubic feet and you're 200 feet from the center, the what do you say? The wind speed is about 75 miles an hour. Is that what we said? Okay. So now, what about partial derivatives? So can we use the contour plot to predict the partial derivatives at this point? So that would be the partial of speed with respect to volume at 2,2, the partial of speed with respect to, that's an S, speed with respect to distance at 2,2. So it's the same thing, except now we're not looking at a table of values. We've got these constant z lines to go by, right? These constant values of z. So the partial with respect to volume would be So you can go to the next. So there's kind of different ways to do it. We'll just go to the next line, right? So going to the next line, that'd be what, increase of 25 for an increase of what volume? 0.7. And then coming from this side, same for an increase of 75. This is about an increase of also 0.7. It's about the same, right? So then we say the speed increases by 75, right? 25. So we're saying to go from one line to the next is a 25. And then this is increase or decrease? Going this way. This is increase, so plus 25 over 0.7. I have no idea what that is, whatever it is. Was it? 250 over 7. Yep, that's what it is. All right, and then this way. So now we're going to look at the partial with respect to distance. And we got kind of a variation here. So this is what? 0.5 feet. And this is like 0.3 feet. So maybe the average is 0.4 feet. Is that right? That's the denominator, right? So I'm changing 0.3 in the y down here and changing 0.5 in the y for a change of what in wind speed? 25? Negative 25. Do you see that when you go up in the y direction, z's are going down, so you need a negative rate of change. So as you're doing the same thing, you're looking to kind of average out the change in the independent for a change in the dependent, which is change in the dependent would be going from line to line, right? Contour line to contour line. Change in the independent would either be along your x-axis change or along your y-axis change. So it's the same thing to do those estimations. So where those numbers come from makes sense. Okay, so now I want to change both of them at the same time in equal amounts. So how would we get the change in wind speed for a change like that? So now I'm saying change in, I want a change in speed would be what? We might go over a little bit. So change in, this is important though. Change in speed is, how would I get the change in speed due to, this is changing both now, right? Yeah.
You could put the change going up over the change going that way.
Yeah.
Assuming we know like how long the diagonal line is, you could just take that times the cosine of the angle it makes.
Okay, you're jumping ahead there. So what did we do last time? If we wanted the total change in our dependent variable for, yeah, so we want the partial of s, right? With respect to x, or with respect to, what's that, v, times what? Times the change in v, right? Plus the partial of d times change in d. Right? Because what does this number mean? It means given any change in volume, the change in speed will be that rate of change times the change in volume, right? We're saying that over and over again. Given any change in distance, the partial with respect to distance, or the change in speed will be the partial of speed with respect to distance times that change in distance. So I'm just using those meanings of those rates of change to set that up. Okay? So what kind of vector operation is that kind of like? multiplying, multiplying, adding. Isn't it the dot product? So I'm going to make vectors out of this. I'm going to make a vector of the partial derivatives. And I'm going to make a vector out of the changes. The change in volume and the change in distance. Is it okay? So now that's the same, right? The dot product of those two vectors is the same as... And that dot product is going to give me how much the wind speed changes for an equal change in volume and distance. Now, if we had equal changes of volume and distance such that the overall change, say delta, was equal to 1, then wouldn't this change in wind speed also be the rate of change? If I make the amount of overall change in that direction right there, if I make that 1, then this would not only be the change in wind speed, but it would also be the rate of change of wind speed for that proportion of changes in volume and distance. Wouldn't it be? So if the magnitude equals 1, then that is a rate of change. Besides also being the amount of change, right? Being the amount of change of speed, it also becomes the rate of change. Yeah? So how can I write these changes of v and d in proportion to one another so that that distance is always 1 for any proportion of v and d? Now this is where it comes in. Cody? Yep, and if that has a length of 1, and now we want any proportion of v to d, so like in this direction or in this direction. So any proportion of a change in v to a change in d such that the overall change is 1, what could that be then? Say like this is theta. That angle is theta. How do I get a vector of length 1 if that's theta? Make my dv equal to cosine theta. Make my dd equal to sine theta. And that always will have a magnitude of 1, no matter which way we're doing. And so then this now is the rate of change in direction of theta. So at first we said there were how many rates of change? Given a multivariable function of 2 variables, we said there were 2 rates of change. But now we can take any combination of a proportion, any proportion of those 2, and we can get how many rates of change? What's that? An infinite number, right? So given a proportion of a change in this case v to a change in d, which would give a direction, we can get the rate of change in that direction. Okay? So this is called the directional derivative. There's not just 2 derivatives for a multivariable function of 2 variables. There's actually an infinite number of them based on taking changes in your 2 variables in proportion to one another. So that's just, we're going to explore the directional derivative in detail on Monday. That's a little intro. Thanks for staying late.